Okay, so this talk is about how eBPF enables Linux networking. So basically, the idea is you all probably know about eBPF by now, and what does eBPF brings to networking? Hello. Uh, is this audible? Sure. So this talk is about how eBPF enables networking and what can you do with different type of eBPF frameworks to accelerate the Linux networking. So the agenda of the talk that I kept is something like this. Basically, I plan to start with why eBPF, but I guess you guys already are up to speed with what eBPF is, so we don't need to cover that. But for the following things that we'll cover after this is, the first thing that I want to talk about is why is Linux kernel even slow, or what makes the Linux kernel slow for networking, so that we have a problem. We first establish that we have a problem that we want to solve with eBPF. Next, we'll see how can eBPF solve the problem with the kernel data path. Okay. Okay, thank you. Yeah, so how can eBPF solve the problems with the kernel data path? Essentially, what does eBPF brings in that the certain characteristics that eBPF brings in that can solve these problems? Finally, we'll basically move forward and look at what does eBPF do in the context of a larger cloud environment, particularly in a microservices cloud environment where everybody seems to be moving these days. In hindsight, like Kubernetes environment, Openshift environment. Finally, I'll basically like to end the talk with two things. What is, when you go into networking, there's not only just high-speed networking that you can do with eBPF. What else can you enable with eBPF in the area of networking? And how, what do you do from here? Like, where do you start contributing, or where can you see contribute further? Okay, so is this logged? Yeah, sure. Yeah, so basically this is a small anecdote that I want to start the talk with, that you guys know eBPF is awesome. You guys will know that Linux kernel is slow. And in this talk, I want to show you how to make the packets flow. So I'll just skip over these things on why eBPF is something that we need. And I'll start this session by saying what is so slow about Linux kernel networking. So if you look at Linux operating system, there's lots and lots of things that are good with Linux kernel, but what are some of the things that are not so good? First is the kernel has been developed over so many years, it's a big monolith. So there is too much bloating of source code that is there in the Linux kernel. Too many layers have been built up, and it is very generic design to incorporate everything and anything that people want to contribute. So like still Linux has code which can process the ATM protocol, which is not needed. It's like ages in the past. What this brings is, basically affects the visibility that as a developer or as an engineer you have in the Linux kernel to make any change, to bring in new changes. And for any specific use case that you want to do in the Linux kernel, you have to see where do I fit in, where do I cut in, and what do I do. All of this entails to very low feature velocity, which means that any change that you want to do takes in forever to bring in. And even changes previous to eBPF, the changes that you were to bring in to Linux kernel were used to be through modules. And modules also used to take like months and months to build. While with eBPF, you can write smaller programs that you can directly execute to see the gains. So let's start by looking at what the path of a packet in the Linux kernel looks like. So at the bottom, you have the hardware, where you have your network interface card. The hardware has its own hardware receiver and transmitter queues from where it receives the packet. The hardware sends this packet via DMA to the device driver. Now, device driver is the first entry point into the kernel space that we go from the hardware to the kernel. the device driver, after receiving the packet, obviously it receives it on a ring buffer that the driver maintains in kernel memory or in CPU memory. And then driver creates this particular structure that represents a packet interface in the Linux kernel, which is called struct escape buff. This is the structure that gets passed on between each and every Linux layer and represents one packet that flows through the kernel. On top of the device driver, you have a queuing discipline in the Linux kernel. The job of queuing discipline is to maintain different queues for scheduling the packets in a different sense, for mangling the packets, and for moving the packets from one queue to a different queue. Queuing discipline maintains different queues for receiving and transmitting, as same as the device driver. On top of this, you have the code written for each and every layer that you were to interface with. So like your standard OSI model, you will have the layer 2 code to work with the Ethernet frame, layer 3 code to work with the IP packet, layer 4 code to work with the TCP segment. Finally, you have a socket interface that cuts through the kernel to user space, and on top of the socket, you have the application which sits in the user space and receives the packet. So one single packet that you were to send to an application has to traverse all of these layers to be finally received. The problem that this brings in is, if you are designing a network function on top of Linux, the packet has to traverse this entire source code before even reaching the application. So if I'm, let's say, writing a filtering rule in user space, so I'm designing a firewall, I write code for the firewall in any language that I want. I run it on top of Linux. When my firewall is receiving a packet, the packet is coming from the entire stack up, make a decision. If I want to let the packet through, I want to send the packet back through the entire queue and send it forward. This whole overhead, there should be something that we can do about it. And basically, you don't even need to take my word that this overhead is there, that the kernel is slow. There have been papers which show, like the one that I have referenced here, which show that just the single data copy from kernel to application buffer and from basically the driver to the kernel buffer can take almost as much as a half of CPU cycles consumed for processing a packet. The code that is there for handling TCP streams, for handling the escape buff mangling and escape buff management allocation, again takes up very significant time in the CPU. And the reason this exists is because the kernel has a design philosophy, or the Linux kernel obviously has a design philosophy of one glove fits the hand. And that design philosophy doesn't always work when you have different type of network characteristics from the network traffic. So if you have larger flows versus smaller flows mangling together, one of them is going to get squeezed out, and one of them is going to experience low throughput, high latency, and many bad things. So what you need here essentially to improve this is a design where you can identify different type of network streams, you can identify different type of network characteristics and design your solution based on the network that you want to absolutely gain the performance that you need. So this now moves us to the next section on how can eBPF solve the kernel data path, or how can eBPF solve the problem of slow kernel data path. So let's look at the network stack again. So this time what we'll look is how many eBPF hook points are there in the network stack, and where in the different points in the network stack can we hook and can we generate our own custom functions. So starting from the top, I'm not listing the user probes here because we are talking about the network stack. So you have at the socket layer, you have sockmap and sockops hook points which receives a socket object. You can work on the socket object, do any sort of connection mangling, connection information change. On the TCP layers, you have K probes for different functions. On the TCP IP and Ethernet layer, you have K probes, or you have C groups, and these are hook points that are lower level at function level and at a larger C group level as well, where you can hook into individual functions as well as individual C groups. At the TC layer is when we see the main performance gain from eBPF coming through, which is the eBPF TC hook, where TC, the traffic control subsystem of the Linux, provides eBPF execution in the queuing discipline via there's a mode called the direct action mode, with which you can directly execute eBPF program when a packet is received in the TC queue or when the packet is going out from the TC queue. So both at the receiving and the transmitting end. At the driver layer is what you have the XDP hooks. So XDP provides execution of eBPF programs directly in the driver. And so if you see all of these layers, basically the design is move execution as close to the point as you want, wherever you want to execute something. And obviously at the NIC layer, then again you have the XDP offload hooks, so there was a question from somebody on how P4 works with eBPF. Well, some of the NICs actually enable eBPF execution inside the P4 engine, in the NIC engine. Mellanox does that, Netronome does that, and there are compilers, obviously, as Brendan mentioned, which convert eBPF programs to be P4 programs, and they directly execute in the NIC, which is called XDP offload hooks. So we'll see each and every hook point in more detail. But one thing to see here is in the entire stack, you have hooks everywhere. So you should take a look at this picture holistically, in the sense that based on your use case, which is the primary point that you would want to connect at. So let's start with the socket layer. So at the socket layer, you have a eBPF SOCOPS hook, which you can hook directly just before a user is sending a packet or just before a user is receiving a packet in terms of a socket connection. What the program receives is a struct BPF SOCOPS. So the program that you would write would look something like this. The struct SOCOPS internally contains all the information about the connection establishment, connection parameters, connection transport, and which you can use and change as and when required. Moving below, on the TC layer, you have eBPF TC hooks, which receive struct skbuff. Now this skbuff, as I mentioned, is the low-level data structure that represents a packet in the kernel. So at the TC layer, you receive struct skbuff, and again, because TC, the queuing discipline is maintained both for the receiver and the transmitter queue, you have eBPF programs that can hook directly at both the queues. And a program here that you would write would look something like this, where you define a program which receives struct skbuff, and based on your skbuff, you would take some decision. In the driver layer, you will have the XDP hook, which implements eBPF execution currently only in the receiver side. And the reason, the XDP hook in the driver actually accepts not the struct skbuff, but struct XDP-MD. And struct XDP-MD represents a raw packet that comes in to the kernel subsystem directly from a NIC. So when a network interface card would DMA a packet to the driver before even allocating a struct skbuff would create a XDP-MD structure on top of it and pass it to the eBPF program. What this gives you benefit is, without even allocating any kernel data structure, you can take decisions on the packet, whether you want to change it, divert it, or drop it, or move it forward. And obviously, because what I mentioned is driver needs to execute this eBPF program, you need explicit driver support for this type of XDP hooks. And most of the drivers these days have implemented this XDP support. A program that you would write would receive struct XDP-MD, something like this. Even in this XDP, you have different type of hook points at just the XDP layer. So what I just explained to you, where you would need a driver support from the driver subsystem to execute an eBPF program is called a native XDP hook, where driver fires the XDP just after the packet arrives. If the driver does not have a support for something like this, what you would do is you would implement something like a generic XDP hook, where the driver allocates an SK buff, but then the kernel runs eBPF program on top of the SK buff that was created by converting the SK buff to an XDP MD structure. So your packet comes in, it goes to the driver allocates an SK buff, but it's not actually at the TC layer, just below the TC layer, the SK buff gets converted to XDP MD, and you again execute your XDP program that you implemented. This obviously incurs some penalty, as I mentioned before, where you would allocate an SK buff, and the SK buff allocation penalty is something that you have to take. And finally, if you were to move everything down to the NIC, it's called XDP offload hook, where XDP program directly gets executed inside the NIC or the P4 program, and this obviously needs special support from the hardware to be executing these programs. So I think we have covered quite a bit of these things. Any questions at this point? I mean, I don't want to move super fast. No, XDP is also eBPF. Yeah, XDP is also eBPF hook underneath. XDP is or Express Data Path runs an eBPF program. The term Express Data Path is used because it's a separate subsystem that is implemented in the driver to provide you very fast network access to raw packets. That's why it's called. Sure. No, right now you execute full eBPF programs in the XDP layer also. So it depends basically. Some network cards enable support for you to directly offload your eBPF program. So they have eBPF execution subsystem. You would transfer the eBPF program to the NIC, whether they would execute it directly or they would transfer it, translate it to P4 and then execute is up to the network.
And P4 can is expressive enough to cover all of eBPF.
There are basically cases where they would provide some restriction on the language that you can basically offload to the hook, offload to the network card.
Okay.
Rust does, I'm not sure if Rust has a support for XDP. So Rust is a language, XDP is a layer at the kernel level. If you, what you mean is you can write eBPF programs in Rust and then run XDP. So Rust is, the level at which Rust executes it is at the user level, where it enables you to write the eBPF programs, load them, manage them. So that level of management you can potentially do in any language. You can write Golang language code to manage the eBPF programs and then execute them at any layer in the kernel. Not just XDP, but any layer in the kernel. Yes, it involves copying certain structures over to the XDP MD. So XDP is less flexible because you work at the raw packet layer. You have not even read the packet metadata enough to know what is inside the packet to even create the full data structure that the kernel creates. That's why it's essentially, but the level of flexibility that XDP provides is almost equal, because you can access the entire packet data from there. So you can parse the metadata yourself to know what is inside the packet. I think the difference comes at the level of what BPF helpers are available at the XDP layer versus what are available at the TC layer. Yeah.
So if you are using a generic XDP implementation, the kernel will convert from escape to XDP, right?
Yeah.
How does this work in, let's say, VET? So VET also has support for virtual Ethernet card implementation, has support for XGP.
VEth now has native implementation for XDP native, which means the virtual Ethernet driver that your kernel runs supports XDP. So it is all virtual, but the driver supports XDP, which means the driver can act like that.
So there's no SKB to XDP conversion behind the scenes in.
So what the driver essentially does is, if you want to transfer a packet from your host Ethernet card, essentially let's say your H0 to a virtual Ethernet, that driver has a support for you to not need the conversion. So you can directly redirect a packet from one interface to the other interface without doing the conversion. That support has been added in the virtual Ethernet stack.
Okay, so there's no overhead as such, conversion
This
from
overhead
XDP.
is not.
Okay.
Should I?
Interrupt handling, all this actually doesn't happen in the BF place, right? Like for example, a pod to a underlying root namespace communication.
So I'll cover the pod to a root namespace communication later. But to answer your question, basically what benefit does VEth XDP provides compared to VEth TC is that if you have to make a decision at the VEth level on whether the packet belongs to this pod or not, you can make that decision at the XDP level without escape of allocation versus involving TC. So it's slight benefit that you get at that layer. Otherwise, even if you were to execute XDP program at the VEth layer, it would be executing as an XDP generic program.
I'm looking at it from the pod to.
I'll cover that.
It's like a pipe, right?
Sure. I'll cover that. Sure.
That is that equivalent to P4 programming? I mean, we can match the P4 programming. How it will be?
In terms of functionality, you can.
Okay.
But the P4 programming language is a different language then.
Yeah, correct. It's a different language, but it's a substitute for that we can say, right?
Sure. Yeah. I mean, you can do translation. I don't know how compatible they are, whether all functions of P4 can be done in eBPF or all functions of eBPF can be done in P4. I'm not 100% sure of that.
Okay.
But in theory, you can do that translation.
Thank you.
So if you see the design philosophy that we are going with here, basically moving each and every hook at the lowest layer, what we are trying to do is whenever we execute any program at any of these layers, we want to cut through the kernel. So in this entire stack, I want to basically execute a program at the XDP layer, then move the packet directly to the socket layer or the user space, bring the packet back from the socket layer to the TC layer and send it back outside. So one of such execution engine that the kernel supports is called AFXDP, which is a raw socket that gets directly exposed to user space application. So whenever a packet comes in through your NIC to the driver, it gets directly transferred from the driver to the user space via this AFXDP socket. What this provides is a zero copy mode from the driver directly to the user space, where the driver, you can sort of rewire the pointers directly to the user space application, telling where the packet belongs. And this provides very high benefit because this is full kernel bypass as compared to the other hooks where you would do kernel bypass at a more step-by-step level. Now with all this knowledge, let's see how we would write our programs differently. So if you remember previously, we had written a eBPF firewall in user space, where what we had done was take the packet to the full user space and written a firewall there. Now if I'm writing an eBPF firewall after all this knowledge, what I would do is I would install a program at the TC hook. I would execute my filtering logic inside the eBPF program, and if need be, I would drop the packet directly at the TC hook rather than the packet taking full TCP and socket layer penalty. For XDP, let's say if I'm writing a load balancer, similarly, what I would do is, let's say I'm writing a layer 3 balancer or an IP load balancer. What I would do is I would take the packet, take it in the XDP layer, read the packet metadata to know which IP it is, where do I want to load balance that packet to, and then directly redirect the packet back on the same NIC. So rather than going through anywhere through the kernel, I have executed that whole load balancing logic at the lowest level inside my stack and done the same behavior, executed the same behavior as I would execute. So this so both of these programs, by the way, exist. So the load balancer, if you want to see, you can see this project called Katran by Facebook, which is a load balancer implemented in XDP. The firewall is a project by Redhat. It's called Ingress Node Firewall. It's a project by one of our group where we implement a firewall at the TC layer. And so finally, one more thing which I want to show here is not just one single hook point. How do you combine different hook points? So if you have different application characteristics that you need. So let's say I want to implement a packet tunnel. What I want to implement is a packet comes into my network. I want to implement a tunneled packet comes into my network card. I want to send a decapsulated packet to the Ethernet, and I want to make sure that whatever packet goes out from my pod is encapsulated with a tunnel. So what I do is packet comes in, I write an XDP program in my driver. What that XDP program does is it decapsulates the tunnel packet and redirects it to the virtual Ethernet of the container. When the packet goes out from the container, I write another program at the TC layer. Now this time TC layer, because XDP doesn't support transmitting queue. So at the TC layer, I intercept the packet, run the eBPF program, encapsulate the packet, and redirect it back to the network card. So one thing which is not shown here is, so you're seeing this as one single stack, but think of it differently, because the NIC that is executing, the NIC driver that is executing this program is a hardware NIC that you have. So something like ETH0, while the TC program which is executing your encapsulation is at the TC queue of the virtual Ethernet. So these are basically different queues. So there is a queue at the ETH0 layer, there is a queue at the VF layer. So by implementing these separately, you can get this type of benefit where you can transfer the packet from one hook to the other hook and design your network function as you want. So before I move on to the next, oh sure.
Just clarification. What's the difference between XDP hook and XDP program hook?
XDP program hook.
I think in your XDP program, you have mentioned the thing that's seen as a hook. You can just clarify that part.
Okay. What I mean in the figure is, in the XDP hook, you are running an XDP program. It's just that. There's no difference. XDP hook is the same as the XDP program.
The user thinks that the XDP program is a different hook.
No. It's an XDP program running at the XDP hook point.
Correct. And the second thing is, can you confirm that you can do kernel bypassing by using XDP?
Yes. So the AF XDP socket that I showed is full kernel bypass. So it's akin to DPDK, if you know DPDK. Sure. Any other questions? Sure. You can run it at any layer. It's to demonstrate basically the different hook points that you have. And the other reason is the firewall that we have been running in the Red Hat subsystem is run on Openshift platform, and on Openshift we need a pod level firewall. So not always we have XDP available everywhere. That's why to be more generic, we implement it at TC layer. Depends on what benefit you need and from which type of software. A load balancer needs to run at much faster rate. Firewall probably doesn't.
You mentioned about that load balancer. It will be captured at the driver level, right? Or after getting it to the driver level. So if the packet is MAC-sect or IP-sect, so how that will be handled? Because that particular key, right? Key needs to be present in this.
Yeah, for IPsec and other type of frameworks, you need to basically provide your program with the key. You need to make sure the key is available to your program.
Okay, that was my question.
You need that, yeah. Okay. So with this knowledge, now let's move on to the next part where we see how can eBPF work in the world of microservices, or what does eBPF bring into the Kubernetes environment. So I want to start by showing one example of how intra-pod to pod communication works in one node. So the diagram that I'm showing you is a single host where you have a bridge connecting to virtual Ethernet. The Ethernet pair of those virtual Ethernet is attached to two different pods which have two different sockets which execute any bit of networking function, and the underlying CNI, let's say, for example, is Flannel. So if you were to look at the overhead of the standard kernel stack execution that is there in this scenario, is when you pass a packet from one pod, first it has to traverse the network stack of the pod 1, because it's in a separate namespace, a separate network stack is there. So pod 1 namespace, then the Linux namespace where you were to traverse the entire VH and the bridge stack. Finally, the pod 2 namespace. So all of this overhead, what it means is you are incurring multiple copies of the packet as it traverses from the pod 1 to pod 2, and you are incurring multiple traversal through the entire stack as the packet goes from one pod to the other. So how do you improve that? So can anybody tell me how can I improve that with the knowledge that we discussed? Sure, that's exactly what we do. We use sock maps. So let's look at the picture again. So you have two different sockets that are connecting. I install an eBPF program, attach it at the sock map layer. What the program does is it provides one socket to the other socket translation if the two sockets lie in the same host in different namespaces. And what this enables is this direct zero copy transfer from one pod to the other pod in a single host scenario. And the throughput gains that you were to get from this is, if you see in the sock map versus the no sock map case, the sock map case almost doubles the throughput, while almost the latency becomes almost 1.5 times less. So there is enough acceleration that you gain by doing just one hook in the kernel. If I were to extend it for multi host scenario, what I would do is, if the socket, I need to add some sort of socket visibility across the host, and I can use potentially something like HTTP when the packet goes out from one host to the other host. So combining many of these hooks is what we need to do in a larger scenario where we have a larger set of cloud, multiple microservices running. So with that in mind, let's look at the Kubernetes network stack in one single picture. So you have your cloud where you have host ingress and pod to external communication. On top of that, you have the host network of any host that is there in your Kubernetes cloud. On the host network, a CNI would sit. CNI, but something like Flannel or Cilium or anything would sit. There is a service layer which has service ingress and egress. There is a pod layer, and finally there is a containers. And every different layer as we saw in the eBPF hook points in the network stack, at every different layer of the network stack in a Kubernetes environment, you again are presented with the same set of opportunities to optimize for different layers in different scenarios for different use cases. So if I were to do load balancing, I would do it at the lowest layer. If I'm doing pod traffic filtering or any sort of firewall, I would do it at the pod ingress and pod egress layer. And what eBPF brings in is all these functionalities can be implemented in eBPF separately, and they are better suited for future proofing because these are small designed programs. You can write one program, you can change it tomorrow, and as basically again the same philosophy as Brendan mentioned, you can write any program, any different program every week, or use a different program, existing program, different week to get different type of behavior. Another thing that eBPF brings in to this whole world of microservices, eBPF is the one infrastructure for improving the network performance that has full breadth of the kernel data structures and the kernel subsystem available to it. While one side we say that the kernel is bad because the kernel stack is bloated, it has layers, it has too much code, but at the same time kernel has so much to offer that the program can potentially use. Over so many years, people have been trying to implement fast networking. So suppose I am running a Kubernetes cloud for a telco workload in something like an IBM cloud. I need line rate performance. Or suppose I am running same kind of Kubernetes work, high speed workload in, let's say, one of the hyperscalers, Facebook, Google, and anybody, where they would need high speed performance for their own use cases. So on all of these scenarios, to gain line rate for 40G, 100G type of NICs, people have developed software to completely bypass the kernel. Things like DPDK and VPP have been doing these sort of things. What eBPF provides you separately than those is, if you were to basically take the packet and directly pass it to user space, cutting through the entire stack, what that means is you have to implement everything back into the user space. So if you don't have the entire TCP stack available from the kernel, you have to implement the entire TCP stack again in the user space. You have to implement the forwarding logic again in the user space. So what eBPF provides more than the customization of the kernel is the kernel itself. So some things like kernel forwarding table, things like kernel TCP, UDP, and protocol stacks are available to you whenever you want to use them. So finally, the proposition that we share is that rather than building big set of CNIs, which are again becoming monoliths in this networking environment, from where we started, we extend container networking interface. Container networking interface. It's a software that provides networking to a Kubernetes environment. So rather than building large CNIs, which again become monoliths in this Kubernetes space, you can implement small bit of network functions and integrate those at different points in this stack to gain as much customization to the network as you want at a per use case basis even. So this is akin to the discussion that for every use case, even in networking, you don't need to write your own network function. You can potentially use the network functions that exist on the open source platforms like your Solo, Leaf, or even eBPF.io, and combine them, or even GitHub, like combine them and create your own network stack, customize your own network stack. And this is a paper that we had done last year. So any questions at this point? I got a question on CNIs. So SRIOV is not in contrast to XGP. SRIOV, no. SRIOV is IO node virtualization, where you have one network card with SRIOV. You can make it look like 10 different network cards. So one network card has 10 different queues or 5 different queues, and it can potentially provide visibility as 10 different network cards to 10 different applications. So in theory, you get almost individual bandwidth level performance.
That doesn't matter whether it's a virtual card or a physical card. I assign to a network function, right?
Sure.
So similar thing you can do with the XDP.
Yes.
Yeah. So
What I'm saying is you can do XDP even on top of SRIOV. So SRIOV makes sure that the network hardware is divided.
Why? Why is my question? So when today's network functions are happily using the SRIOVs, why is the use case for XDP for them is the question.
So again, coming back to the same point. So if they are using SRIOV, by the way, I think the question that you are asking is if they are using SRIOV, so generally they use SRIOV plus something like DPDK, where they can separate out the hardware using SRIOV and assign individual hardware sub-functions directly to the user space application, which runs the entire code. So there because they do user space networking and full kernel bypass, they get the benefit of almost line rate performance. But again, if you see there also, what XDP can bring you is rather than implementing that whole thing again and rather than getting fixed with frameworks like DPDK, you can execute something in the kernel directly, a small piece of code in the kernel directly, and can gain the same level of performance. The other thing that brings in is the user space networking libraries like DPDK and all, they hog CPU. So you have to basically provide them CPU and they have to continuously poll the CPU for execution. While XDP, because it is natively kernel implemented subsystem, it can be interrupted and it doesn't use that much CPU.
But can they benefit from observability that eBPF allows? Can they leverage that?
So if you are running the entire code in user space, the observability that you would want to use there is something like user space tracing or user space exposing metrics from the user space application itself. So if my entire network code and my application code all is combined into one big application that is running there, then the benefit from observability comes from when the application exposes it, or I am able to poke into the application using some user space tracing. So that's the observability that you can get. But directly with eBPF, unless we go into those user space level tracing, you will not gain eBPF based observability.
Just another question or rather use case that I didn't see in the slide deck was about using or changing the parameters of congestion control algorithms through eBPF bytecode. That is the new, that is now possible.
Sure.
And that possibly allows us to now change or make, application specific congestion control logic. It's now possible. That can also be a possible use case from this optimization. But coming back to, Sridhar, I think in terms of SRIOE plus if you have DPDK, then I don't think from the offloading perspective you have a use case for XDP. But the problem for XDP, the use case for XDP could be from the DDoS protection perspective in that context. That's the only thing that I can see.
Yeah.
So already being used in the DPDK. When needed, you can select the pole mode driver, XTP pole mode driver.
Sure. So the AFXDP subsystem is a Linux kernel alternative to DPDK. Yeah.
Pole mode driver.
Exactly. The AFXDP subsystem is that only. So DPDK is a library implemented by Intel, and this is much more open source in that sense.
So I like the idea about the packet tunnel. And in fact, Cilium has essentially done it generically, right? Like if you use CNI, then you have a direct server return where it eliminates the local legs, wherein if you're transferring packets from one socket to another socket within the same host, it's automatically. So how would this be different? Like, is it the same concept done generically under the hood, or how is this packet tunneling idea different from that perspective?
So it's similar, in the sense. It's basically similar in the sense that whatever Cilium has, so Cilium is obviously adding more and more capabilities to the CNI in terms of what eBPF provides them. And this is a view into basically you can, in theory, build this smaller set of functions, or even I'll come to one more point that even you can extract out functions from monoliths like Cilium and then use them to build your own function like that.
But like you mentioned, we'll lose out on certain things like the observability that you get when the packet traverses, and then the enforcement points, like if you have a network policy, then how would you enforce those policies if you're bypassing the complete?
If we are bypassing, basically, so the idea is that if you are bypassing the kernel at some point, we'll definitely lose out on some of the functionality that there is, but we gain on something else.
Thank you.
I had a question, Dushyant. Yeah. So there are some DPUs and smart NICs which allow you to offload, say, a particular protocol processing, say, transport processing, to the smart device. So how does eBPF allow you to leverage that the protocol set transport layer is processed at the smart NIC, and then application should be able to grab hold of that data directly without involving too much of memory copy?
So if you have a NIC interface where you are essentially offloading the protocol to the hardware card directly, I think that is for a use case where you are executing everything in the hardware to make it much more faster. So whether you have a need for eBPF in that scenario in terms of improving the network further, I'm not sure, but because these guys already run very specialized use cases. But if there is, you can potentially do things like network observability there. So whatever information that the kernel is getting from the packet after it has been processed by the hardware, then you can observe there or improve upon that in terms of, let's say, the socket, or in terms of observing what different characteristics are of the packet.
Thanks. And yeah, like one more question, small question. So extending on Rahul's point about tuning the transport protocol parameters there, like will it help if you have this kind of interfaces with the smart devices?
So if you are basically putting everything in the hardware card, then I think you need to put the tuning of the transport parameters also in the hardware card, because the hardware card is going to be executing all of this, and the hardware card will need to make decision on which type of flow needs to have which type of transport parameters. So the idea with basically you changing transport parameters with eBPF is that at a per flow level, I can make a decision in the eBPF layer on which type of flow I am getting and what decision I want to make in terms of which TCP algorithm I want to run, or where I want to route the packet. So all these things, they make sense when they are in the kernel. If you are offloading everything, you can in theory basically offload the same logic in the NIC as well, which takes a decision based on different characteristics of the network on which parameter to use and which parameter to not use.
Thanks.
Actually, you touched upon the offloading in TC and XDP, right? So, I mean, as a developer, I see like offloading in TC could be little easier, because I mean we have different drivers, and writing for each driver is little tedious. So was there any kind of I mean, from my experiments, I didn't see much of difference from offloading in XDB and TC. Not much. It was like negligible. And also offloading in TC helped me with a few observability. I mean, I was able to have some BPF maps and do much more. So what do you think? Like, do you think offloading at TC itself is better, or do you think like there could be some kind of advantage in the XDP?
By offloading, you mean running the eBPF program at TC versus running it at XDP? There is definitely
TC BPF redirect versus XDB redirect?
So there is definitely benefit to be gained when you run XDP, because as I mentioned, there's easily the 10-15% of the CPU cycle that you consume for allocating SKPF gets removed when you are running XDP. If you can make the decision in XDP, you can lose out on observability at some layer. I'm not 100% sure, but the thing that you mentioned is BPF maps. There are maps in XDP layer as well. So you can export the same level of metrics from the eBPF program in XDP as you are exporting in TC. Can I take this after? Okay. So after covering what eBPF can do for networking, I want to cover a little bit about what extra eBPF can provide for networking. So when you're doing fast networking, what that means is you're processing the packets at a much faster rate. And when you're processing the packets, the thing that you can also do is observe what is happening in the packets. So network observability is a different use case that we have been working alongside networking to monitor network traffic from and to end hosts. The reason you would do network observability is to identify sporadic increases in latencies, identify different heavy hitters. What we do to solve this is previously there were challenges in monitoring the network, as previously monitoring was implemented in switching ASICs. There was special ASIC code and special piece of hardware designed to monitor the network. Now when you move all this into the host level, you have high CPU consumption, which is the issue for these different network observability tools like TCP dump, PMACCT. They are very intrusive to throughput. They basically, some of them copy the full stream and then do monitoring on top of the stream. And these things are expensive. So what we have built is the small piece of eBPF agent that does in kernel data path flow capture. So this eBPF agent sits in the kernel. As a packet comes in, it just reads something from the packet, transfers it back to the user space to export all the observability information as a flow level information and sends the packet again. It's very low level execution on top of the packet, and what it provides is flow level capture and even packet level capture for things like doing DNS monitoring and full packet export in case of specific use cases like DNS payload monitoring and other things. The design we followed to make this faster is to use different type of eBPF data structures. So we use rather than we using a specific array, we use a per CPU hash map where we would pass the data to the user space because hash map provide you much faster access, and a ring buffer in case of evicting these flows. How does it perform compared to how does our program perform compared to others? Is basically, so you see the throughput that our agent gets is much higher. So it's of the order of 1.5 times that of TCP dump and of the order of almost 2.5 times that of PMACCT, and the same that you get for TCP UDP and UDP ingress and UDP egress with a mere 11% increase in CPU consumption due to eBPF. So this is one of the things that we have done. You can check it out. Finally, I want to cover just one last thing, which is what do you guys can do from here? Like, where do you contribute further? So I will briefly talk about one of the work that we have done, which is we have developed a group in IBM Research. We have developed this working group with a lot of different university partners, professors, to develop this thing called tools for eBPF DevSecOps. We are calling it Open. So the problem in this space that we need to look at is, so eBPF tooling right now, what it exists is you have tooling for development like libbpf, BCC, BPF trace. You have tooling for deployment like a kernel verifier, the loader, BTF gen, and finally you have tooling to maintain lifecycle. software like Leaf, Solo, BPFD, and BPF tool, which provide basic compile, check, load, run, and stop. What they don't provide is the DevOps functionality on top of eBPF, which is, can you modularly extract eBPF code or eBPF functions from open source PCs and open source larger network functions or larger modules like Katran, Cilium, and use them by converting from one hook to the other hook and attaching them wherever you want. So this again follows the same idea that your network could be comprising of many small hooks and small programs running at different hooks and running a custom logic in that sense. Or even, how do I interact with my eBPF code? Is there a tooling that is available for me to generically interact with my eBPF code? The other thing that is missing is SecOps. So in this eBPF scenario, you have programs that you download from somewhere and you execute. If you are running a cloud, and that too a cloud that has strong compliance to provide, like HIPAA compliance or GDPR compliance, you have to make sure that the program at times does not execute on particular type of packets or does not view certain type of data because of the regulations. So can I trust the eBPF program that I'm downloading from the internet and loading? Can I trust Cilium, for example, that it doesn't do specific type of operations on my packet? And finally, SRE tools to debug where do things break and how are things working. So in our eBPF DevSecOps environment, we provide this end-to-end environment for eBPF explainability. So we have work where we have done human core annotation. We have ongoing work on AI for code, which uses LLMs to explain what eBPF programs are doing. We have capabilities, helper-based capabilities and user-space capabilities for eBPF programs to monitor and debug. And also at the same time, we have policy-based enforcements for these eBPF programs from the LLM layer or from the runtime layer. We are open to contribution and we are open to working with others. So please join us. Finally, this is Dushyant Behl. That's my email if you want to talk to me. And I want to end the same anecdote slightly differently. That eBPF is awesome, the kernel is slow. One hook at a time, we will make the packets flow.
Awesome.